Hi, welcome to the enzyme kinetic series of videos. This video is part 2 of a two-part series on ligand binding and the Adair model. Now in part 1 I talked about the relationship between the macroscopic dissociation constants and the microscopic dissociation constants in terms of the number of binding sites excuse me, and the number of ligands. This one here is just the reciprocal of this when it's in terms of the association constants instead of the dissociation constants. So we're going to use some of these results and some of the concepts in part 2. So I would review that video if you haven't seen that video. Let me let me motivate this a bit. So here we have a picture of hemoglobin. As you know, hemoglobin is responsible for carrying oxygen in the bloodstream. Picks it up in the lungs and then dumps it in the tissues and then returns back to the lungs to pick up more oxygen. So this is a picture of the protein molecule itself. It has 4 subunits. There's 2 alpha subunits and 2 beta subunits. These subunits have at the center a porphyrin ring. You can see it here, 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 and here, I hope. At the center of the porphyrin ring is an ion, Fe ion. Okay, there's one there, one there. You can't see that one, but there's one there. And it's this that's responsible for binding to the oxygen molecule. So each subunit can bind one oxygen molecule, and therefore each hemoglobin protein molecule can bind up to 4 oxygen molecules. Now it's possible for there to be no oxygen bound, or 1 site occupied, 2 sites occupied, and so on. Now what's interesting about hemoglobin is that it has an odd behavior when it comes to the response hemoglobin has to different oxygen partial pressures. So on the y-axis here I have the percent saturation. This effectively measures the number of sites bound on a hemoglobin molecule. So down here there are no oxygen molecules bound, and up here we've got all 4 sites bound to oxygen. And then this is as a function of the oxygen partial pressure, effectively the oxygen concentration. And we see it has a bit of an odd curve. It's an S-shaped curve or a sigmoid curve. This has functional significance. So for example, in the lungs, where the oxygen level is around here, we see that hemoglobin is fully saturated. In other words, all 4 sites are occupied. This makes sense. Once you're at the lungs, you want hemoglobin to pick up as much oxygen as possible. Now, as the blood moves away from the lungs to the tissues, the oxygen partial pressure drops. And when that happens, of course, you want to start dumping the oxygen into the tissues. And we see that this is done by having a very steep slope here. So as the oxygen pressure changes, even the small amounts, it can dump oxygen into the tissues. All right, and so this is a good thing to do. Okay, so the question you want to ask is how does this come about? How is there a sigmoid response? How does hemoglobin generate a sigmoid response like that? Now this question has been around for at least almost 100 years, and the first serious model that tried to explain this sigmoid response was by Adair in 1925. There have been a couple of other models since then which are probably better, but this is a good one to look at because you can actually fit protein binding data to the Adair model quite well. Now what he proposed was that each binding step, right, so these are the 4 binding steps. So oxygen is bound, the first oxygen being bound to the empty hemoglobin, second oxygen bound, third and fourth oxygen bound. So we have 4 steps, and Adair suggested that the dissociation constant for each step progressively increased from low to high. Okay. All right, so that was the model, and so what we're going to do now is we're going to look at how we can turn that model into a mathematical form that we can use to show cooperativity, a sigmoid response. Now, we're not going to start off with the complicated 4 subunit molecule. Let's start off with a dimer, which will be easier to work with. Now, first thing we need to do is to figure out how we're going to represent the y-axis, percentage saturation. Well, the easiest way to do that is just to use the fractional saturation, F. So this number will go from 0 to 1. 0 meaning none of the sites are occupied by oxygen. If F is 1, it means all 4 sites are occupied by oxygen. And we can compute this fractional saturation just by taking the ratio of the number of bound sites to the total number of binding sites. Okay, so in a single molecule of oxygen, we might have 1 bound site over 4. So the fractional saturation would be a quarter, and so on. Now, for the dimer, this is a diagram of the dimer. We have here the dimer which has no ligands bound to it, and over here we have both ligands bound to it, and then in between we have 1 ligand bound to it, either on the left or the left-hand binding site. Now, as we talked about in the previous video, you can't actually distinguish between these 2 states. All right, they're indistinguishable, and so the only thing we can actually measure is the total. All right, so with that in mind, what's the total number of bound sites? Well, the total number of bound sites is this total, right, whatever that is, plus the concentration of this state, but there are 2 sites per molecule here, so we take the concentration of this, which is P2S, and multiply by 2. All right. Excuse me. So I'll just say that again. So the number of bound sites here is 2 times the concentration of this state. The total number of all sites is easier to write down. So we have to sum up the concentrations of each of these states, P, PS, again the total, and P2S. Now, because each state has 2 binding sites, we have to multiply the whole thing by 2. All right. So with those 2 expressions, we can now form the fractional saturation. Okay, so this is the expression that'll be used to compute this curve. Now, the problem is, of course, we don't have the levels of PS, P2S, and P, but we may have the level of S, and the level of ligand is effectively the x-axis along here. So we need to get rid of some of these terms and put in things that we might know. So what do we know? Well, we can measure the macroscopic association constants, K1 and K2. Yeah, one thing I didn't mention on the diagram, on this side we have K1, on this side we have K2. These are the association, the macroscopic association constants, okay? Notice they're equal here because we're assuming that there's no difference between the 2 sites at this point. So they have the same association constant. And the association constants for K1 is just the concentration, the total concentration of PS divided by the product of P and the ligand. And then K2, the association constant, is the concentration of the dimer with both ligands bound divided by the total concentration of the middle state times, again, the ligand concentration. All right, so we're going to use these 2 now to start eliminating terms in this. In fact, this is a piece of algebra you can do, but basically we can substitute those expressions into the fractional saturation. We can eliminate PS and P2S, and then you discover that you get P terms in the numerator and the denominator, and these just cancel. And so we end up with this. So this is the Adair model for the binding of a ligand to a dimer. All right, so there'll be a different one for a trimer and a different one for a tetramer, which we will look at shortly. But this is basically the Adair equation. So it's in terms of the ligand, S, the concentration of ligand, and these macroscopic association constants. Okay. Now, how do we know if this is going to give us a sigmoid curve or not? Well, we need to convert the macroscopic association constants into the microscopic dissociation constants, because we can actually set values to those. These we can't easily set values to because these are functions of the microscopic association constants. And we know from the previous video that for a dimer, the macroscopic association constant is twice the microscopic constant. And then for the K2, we have this relationship. Now, if there are no interactions, then we know that K1 will equal K2. All right, so K1, let me show the figure. K1 is the binding of ligand from here to here and here to here, and K2 is the binding of ligand from here to here and here to here. Now, if these sites are identical, right, it's as if the two sites are, it's as if the two subunits in the protein are acting independently, then the two binding strengths should be the same, and we can set that up by just saying that K1 equals K2. All right. Now I can substitute. So whenever I see K1, I put 2K little K1. Whenever I see K2, I put a half little K2. All right. So that's what I'll do, and I end up with this expression here. So now this is in terms of the microscopic association constants. I can do a couple of things here. I can pull out the K1, so I get that, and this will factorize, or I can factor this into these into this product. Of course, this cancels with this, and I end up with this expression. Now, those of you who follow the other videos will recognize this to be a hyperbolic response. It's not sigmoidal at all. In fact, here it is. I've plotted it. All right, so here it is. That's the expression again. So if there are no interactions between the sites, in other words, all the microscopic association constants are equal to each other, we get a hyperbolic response. This is not sigmoidal. This is not S-shape. All right, so if there's no interactions, we don't get what we actually see with hemoglobin. Okay. Now, when would we get a sigmoid response? Well, remember that I showed you these, and in fact, if you set K1 to K2 for the case where there are no interactions, you get this relationship between K1 and K2. And this is one of the main points of the previous video that showed that even though the microscopic constants are equal to each other, the macroscopic ones won't, due to statistical effects of the binding and unbinding. Now, it turns out if the second ligand binding is stronger, in other words, this term here is bigger than this one, then we'll see sigmoid behavior. In fact, let me show you that in the next slide. So here now I'm plotting the fractional saturation versus the ligand concentration. This curve here, the lower one, is when K1 equals 4K2. All right, that's the hyperbolic state. If I make 4K2 slightly bigger or bigger than K1, okay, if I make it bigger than K1, then I start to see sigmoid behavior, okay? I start to see sigmoid behavior, all right? So the stronger I make this term, the bigger I make this term, the more sigmoid behavior we see. And this is the case when now the sites aren't identical, okay? In other words, if you look at the diagram, there's the diagram. With the diagram, the binding of the second ligand is stronger than the binding of the first ligand. All right, so that's the case when we have a sigmoid response, when the second ligand binding is stronger than the first ligand binding. Okay, and that's given by this relation here. All right, so let's look at one more example. Let's look at the tetramer. So this is now more like hemoglobin, has 4 binding sites. These are the staged binding reactions, 4 of them. I can write down the macroscopic association constants. Here they are. I've just rearranged them a little bit so the complexes are on the left. Okay. So Ki, the K's are the macroscopic association constants. Now we can combine these. For example, I can take this term and drop it into there. I can take this term and drop it into there, take this term and drop it into there. And if I do that, I can eliminate all the complex terms on the right-hand side. So I'm only left with the complex terms on the left. So I end up with this. All right, that's all I've done. I've just sort of substituted the top one into the second one, the second one into the third, and the third into the fourth. Right, sort of cascaded these substitutions. And when I do that, I get this. So now ES4, the fourth complex, right? Actually, this should be, there's a little mistake there. That should be 4. The fourth state is the product of the 4 association constants times the amount of free enzyme, and then multiplied by the ligand to the power of 4. Okay, so let's keep those in mind. Now the fractional saturation, we have to compute again. This is just the total bound sites again, divided by total all sites. Well, the concentration of all the sites is the sum of all five states from empty up to full, but each state has 4 binding sites to it, so I have to multiply by 4. The numerator is the total bound sites. There's 1 binding site in ES1, there's 2 binding sites in ES2, there's 3 bound sites in ES3, and there's all 4 sites are bound in ES4, all right? So I'm multiplying the concentration of each by the number of binding sites they have. And that gives me the fractional saturation, okay? You can probably see there's a pattern here which we could apply to, proteins with any number of binding sites, okay? You can see the pattern. The numerator contains the sum of all the states multiplied by the number of binding sites, and then the denominator, and then the numerator has as many sites as there are sites that can bind, that have bound ligand, and they progressively increase 1, 2, 3, 4, 5, and so on. All right, so what we're going to do now is we're going to take these terms we had before, for example ES1, and I'm going to substitute it into here and here. I'll take ES2, substitute it into here, and so on, ES4, substitute here and here. And if I do that, I end up with this equation, all right? And this is the Adair equation for a tetramer in terms of the macroscopic association constants. Now, it's not terribly useful for determining the conditions for sigmoidicity. We have to turn these into the microscopic constants in order to do that. So we need to re-express this equation in terms of the microscopic association constants. So this is what we're going to do next, but we'll do it in more general terms, and then we'll come back to this. All right. So let's generalize. So let's generalize the Adair dimer model and tetramer model to any number of subunits. So for example, if there are n subunits, then the mechanism can be written like this, and there's a whole bunch of binding states in between. In each case, I can write down the relationship in terms of the macroscopic association constant. Okay, I can do that trick which I did before, where I cascade the substitutions one to the next and so on, and I'll get these. All right, so these are the generalized association constants, where I've cascaded each one into the next. All right, so the last one is the product of all the association constants times the concentration of the free state times the ligand to the power of the number of ligands. All right, or the ligands to the power of number of sites. So now I need to write a generalized fractional saturation. Again, this is going to be the number of bound sites divided by the total number of sites. So the number of bound sites, okay, let's start with the total, is the easiest one. The number of the total number of sites is the concentrations of each state multiplied by the number of sites. Okay, so remember, if you looked at let me do the tetramer. Let me pick up the tetramer here. Here it is. Hold on, where is it? All right, here it is. So if you look at the tetramer, I had 4 times the sum of the states. Here I have n times the sum of the states. And for the total concentration, I have to add up all the states that have bound ligand. This one has 1 ligand bound, this has 2, 3, 4, and so on. So I have to multiply each state by the number of ligands it has bound. And the last state has n ligands bound, so I multiply that by n. And again, this looks, if you look at the tetramer I did, it goes from 1, 2, 3, 4, all the way up to n. So I then take the ratio of the B0 to T0. This is the fractional saturation. Okay, and then as before though, I now need to substitute in these terms, the ones I cascaded down. So I'll every time I find an ES1, I'll substitute in that. Every time I find an ES2, I'll substitute in that, and so on, all the way down to ESN. Okay. All right. So, for example, the total, right? The denominator ends up like this. So each term I've substituted in one of those terms you saw before. So this is where now we make a change. We change things slightly. We want to now replace these macroscopic association constants with the microscopic ones. And this is where this result that we had in the previous video becomes important, right? This one in particular. I've repeated it here. So recall from a previous slide in the previous video, the macroscopic association constants are related to the microscopic ones with this form. So what I'll do is every time I see a K1, I'll substitute in this. Every time I see a K2, I'll substitute in this with the appropriate change in I. Okay. So if I do that, if I take this T0 and I substitute all these in here, I end up with this unwieldy equation. Okay. All right, note this isn't a mistake, that's correct. It's worth doing this. This is not a difficult piece of algebra to do. You'll get this expression. I can condense this down, actually. You can pull various things out, and I'll end up with this, okay? I can do exactly the same for B0. So remember B0 was this, and I can substitute in each of these terms. And I end up with this. Notice that the E, so when I take the ratio, the E0s will of course cancel. All right, so I take the ratio and I end up with this. This is just the ratio. It looks pretty horrendous, but we can show an example where let's set n to 4. So if I set n to 4, I have to compute all these factorials and this product term, this sum term, not forgetting this n here. This n here appears here. The numerator turns into this, the denominator turns into this. This is for the tetramer. So now this is equivalent, let me just find it here. This is equivalent to the tetramer expression we derived before, but this one was in terms of the macroscopic association constants. This one, though, is in terms of the microscopic association constants. Okay? All right, so this is the result we want. Now we're going to have to figure out when would this show sigmoid behavior and when would it show hyperbolic behavior. Well, as we did before with the dimer, if all the sites show no interactions whatsoever, they're all acting independently, then each of the K's, K1 should equal K2, which should equal K3, which should equal K4. Okay, so what I'm going to do is I'm going to do just that. All right, I'm going to set all the microscopic constants are equal to each other, so there's no preferential binding, and I end up with this. I've expressed it in terms of the K1. Okay, it turns out you can factorize the top and bottom. Not a super difficult thing to do, but you can use Wolfram Alpha if you want to do that. But I end up with this. This 4 here cancels with the 1/4 there. This one cancels with one of these. Sorry, this 10 to the 3 cancels with all 3 of these, so I left with one of those, and I end up with this. This, of course, is hyperbolic behavior, not sigmoidal behavior. So again, it shows that if all the microscopic constants are equal to each other, i.e. there's no preferential binding, no difference in binding between all the binding sites, I get hyperbolic behavior. Now I can show you, if I plotted that, I'd get a hyperbolic curve. Now, in order to show sigmoidicity, all I have to do is make sure that the microscopic binding constants are different. So in fact, they progressively get bigger. So K4 should be bigger than K3, and K3 should be bigger than K2, and K2 should be bigger than K1. So I just set them here. I set K1, 3, and 4 to 1, 10, 20, 30, right, for n equals 4, and I get a sigmoid response. Okay, so this model works. That is, if the binding constants progressively get stronger, as more and more ligand is bound, we will get a sigmoid response. Actually, this fits quite nicely hemoglobin, the hemoglobin data, but there are other things about hemoglobin that don't quite work, and so this model isn't exactly correct when it comes to hemoglobin. There are better models, which we'll return to in a different video. Just the last thing to say, again, to remind you, if all the constants are equal to each other, let's say K1 is 1, K2 is 1, K3 is 1, K4 is 1, I'll get a hyperbolic response. right? Meaning there's no interaction between the sites. Anyway, I hope that helped a bit. If you have any questions, let me know. And goodbye for now. Thank you.